Okay, guys, so today we're going to talk about a Hess cycle, which is another technique for determining enthalpy changes. And so let's go ahead and get started into it. How you are going to see this, for the most part, is like this. You will have a set of reactants going to a set of products, and then below you'll set up the combustion products of the reactants in the original products. And so this is going to be the Hess cycle, and this is how you will normally set it up. It's not the only way to set up a Hess cycle. You can actually have other little steps in here as well. But the basic Hess cycle is like this. And here is what is important for you to know. Now, if you want to know how we come to this conclusion, come talk to me in class, and I'll explain to you in detail how it happens. But if this is our starting point, if the reactants are our starting point, from our starting point, we have two arrows leaving in two different directions, one going right, one going down. If you follow along this pathway, then we get to the products, and then the arrow just continues on. It just turns and comes down here to the combustion products. And then on the other pathway, we have we go to the just a one step to the combustion products. And then at that point, we are at the same position. We're at the combustion products via two pathways. And remember, Hess law is talking about pathways. It doesn't matter which pathway you choose, the answer, the enthalpy change will be the same. And so that's what you'll be doing most of the time. You'll be doing these two pathways. And most of the ones you're going to see, the pathways will be going to the right and down, and the other one will just go down from the reactants. Although it doesn't have to, the arrows can be different. The important thing is this: when the arrows change directions. So here we got an arrow going to the right. The arrow just continues; it just turns, and then we get to this point. If we kept on going, we would face an arrow that's going in the opposite direction. And here's the thing: is that this step one, and step two, and you could say this is step three. Step one plus step two is equal to step three. 1 plus 2, the arrows in the same direction, are going to be equal to the arrows that are in the opposite direction. And so that is how you're going to set up a Hess cycle. As long as your arrows in the same direction, you add them. When the arrows flip around, then you equal that side. So that is how you're going to do a Hess cycle. So let's go ahead and get into an example. All right, so here's an example problem to determine the enthalpy of formation. We want to determine the enthalpy of formation of C2H2 given the following enthalpies of combustions for C2H2, carbon, and hydrogen. And so go back to what we did a few days ago about the reactions for the enthalpies of formation. So we want to form C2H2, then we're going to form it from its elements. The elements of C2H2 are carbon and hydrogen. Those elements in their standard states are carbon in the solid form, and hydrogen in the gaseous form, which would be diatomic. So there is your enthalpy. This is your change of enthalpy of formation. Now, remember from the setup that we talked about a second ago, that you're going to have reactants to products, and then below it you're going to have the combustion products of both the reactants and the products. And so here's how that works. We're going to form the combustion products of C2H2, which are going to be carbon dioxide and water. Because when you burn a hydrocarbon, you get carbon dioxide and water if you have complete combustion, which we're going to assume here. Now, we have to add, oh, sorry, go back for a second. We have to balance this reaction. We didn't balance our initial reaction. So we have two carbons and two hydrogens. We have two hydrogens here. We need to put a 2 there because we want to make 1 mole of this here. Now, to produce CO2 and water, we have to balance this as well. So we have 2 hydrogens, which they're located here, and we have 2 carbons, so we need to put a 2 in front of the CO2, and that gives us down here in this section 4 plus 1 oxygen from right there, and so that's 5 oxygens. So we're going to add to it 2 1/2 oxygens to balance that out, 2 1/2 oxygens. Now, remember that combustion is to burn 1 mole. So we're burning, there's a 1 coefficient here. We're burning 1 mole. So that's how that's going to balance. Now we need to burn these over here. So 2 carbons would form 2 carbon dioxides. That needs 4 oxygens. So we need 2 O2 molecules right there. and then to burn the hydrogen into water, that needs 1/2 of an oxygen molecule. So 1/2 of an O2, because we only need one oxygen right there. One oxygen, so we need half of an O2. That's one oxygen. Okay, all right, so there is your setup. And now we just need to do the Hess cycle. And so if you remember the Hess cycle, we're going to follow the arrows. We have one pathway starting here and going around, and the arrow just simply turns and goes to the combustion products. The other pathway is split among two pathways, but it's still just a pathway that's going down here. And so the arrows in this direction are going to equal the arrows in this direction. And so let's set that up. We're going to have the enthalpy of formation, that's right here, the enthalpy of formation plus this enthalpy of combustion right here. So what is that? Well, that's the enthalpy of combustion of C2H2. Go up here to our data, and there it is right there, the enthalpy of combustion of C2H2. So plus a negative 1301 is going to be equal to these enthalpies of combustions. So the enthalpy of combustion of carbon is negative 393. Now, you have to be careful here because you're burning two carbons. So this enthalpy of combustion of negative 393 is going to be multiplied by 2 because we're burning two carbons, not just one. This value here is negative 1301. We'll just plug our numbers in. This value here from hydrogen is negative 286. And now we're going to add the other half of that pathway, which is we have one hydrogen, so just one of the 286s, negative 286s. Add that, and there's your setup. Delta HF plus negative 1301, so this pathway, delta HF plus negative 1301 is equal to the other arrows. 2 times negative 393 plus negative 286. And that will get you a delta HF equal to negative, I'm sorry, not negative, positive 299. I'm sorry, 229 kilojoules per mole. Okay, that's a Hess cycle. They're all really similar. One pathway equals the other pathway. Just make sure that you can balance out. And you'll use data like this to guide your setup. But in general, reactants to make products, and then below that do combustion products. Not the only way to do it, however.